Let's make a slideshow out of it. From beginning. There we go. There. All right. So chapter 3 is on stoichiometry. Fancy name. Stoichiometry comes from a German word that means countable. And it refers to the way that we use balanced chemical equations to budget where the reactants go. You put in reactants, certain amount of reactants, they come out the other side as products. How we keep track of those is called stoichiometry. Okay, the problem is, and it's the same problem that the scientists in Germany, well, Europe had in 1865 when they met at Karlsruhe, Austria, Karlsruhe, Bavaria, to try to figure out why they couldn't fix their chemical reactions. Universities, companies, everybody was having trouble. The problem was their budgeting was based upon mass only. They had no concept of individual atoms and molecules, how they react. Now, they knew they existed. They just didn't have a way to track them, to keep track of them. It wasn't until Avogadro came along and proposed his theory that the light bulb started going on and they figured it out. The basic problem is, if we're going to use atoms and molecules to account for where reactants are going and end up as products, we got to be able to count them. We got to know how many there are of each one. But we can't very well count atoms and molecules because they're too small. So we have an alternate method. We count the number of atoms by weighing them. And the way you do that, let's see, I'm going to get my remote out. Oops, wrong way. So I don't have to keep stepping up to the computer. There we go. All right, so let me nail down that cursor over here. There we go. Okay. So the way we count by weighing is, first of all, we have to assume that all the objects that we're counting, atoms, molecules, whatever the case may be, are all identical in terms of their mass. If they're not, but they're close, then we have to take an average, know an average mass. Come on. Is that it? It's just slow to respond. Okay, so for example, say we have a pile of marbles that weighs 394.8 grams. We know that for a fact. But we don't want to count how many marbles there are. We just weighed them. So we need an average weight for each marble. So we take a subsample, take 10 marbles and weigh them. So then you divide 37.6 grams by 10 and you have an average mass, 3.760 grams per marble. Then this is a unit conversion problem. 394.80. We want to convert that to the number of marbles. So we want to cancel grams and leave us with marbles, right? So we have 10 marbles and they weigh 37.60 grams, right? Grams cancel, and that's the total number of marbles. So like I said early on, A lot of the problems in chemistry can be solved with dimensional analysis, conversion factors. As long as you stay within the parameters of the physical world. Come on. There we go. So there we find that we have 105 marbles. Of course, always recognize that there could be some kind of error. Remember, that's an uncertain number. That's an uncertain number. So it could be 106, could be 104, whatever. But it's closer than we would get if they were really small, like atoms, and we tried to count them. That'd be impossible. We don't have the equipment for it. So we count atoms by weighing them. Right? The problem, another problem, is that we need a fixed standard for the weight of our atoms. So what scientists finally settled on was something that was very easy to isolate in pure form. And they picked the carbon-12 isotope. That's most of the carbon in our world is carbon-12. So isolating it from the other should be fairly easy. Besides, the people who do this kind of work and isolate isotopes and weigh them and all that stuff, that's all they do. So once they get the numbers for us and get us to a certain point, then we can take it from there. So we don't have to get down in here in the weeds and do all this ourselves. But the standard is the carbon-12 isotope. And what we're saying is that one atom of that isotope weighs 12.000 atomic mass units. Okay, that's fixed. Everything else is compared to that one. Now, how do we compare other atoms to that one? We need Avogadro. Remember, have I shown you this? Avogadro's two gas containers. Yeah. So if we have carbon-12 in this one at a certain temperature, a certain pressure, certain volume, and we put another one, we put a different element over here with the same conditions, then we know that exactly the same number of particles are in each one, right? So if this is the mass of carbon-12, and this is the mass of whatever, then we know that the difference in the masses of these two containers is due to the individual differences in mass of the atoms. That's how we compare the atoms from one to the other. And you do this with several different elements. And once you get a good idea of the mass units for other elements, then it's easier to compare the rest of them to the ones that you've determined. Okay? Because in order to get carbon-12 into a gas, it takes a lot of energy, and the temperature is going to be really high. But that's how we compare them. So that means every other isotope in the periodic table is a fraction of a number, right? It might be, let's see, example, oxygen. If we say oxygen, we want the isotope oxygen 16, right? If we write that like this, we're saying that it has 8 protons and 8 neutrons, right? But compared to the carbon-12 isotope, which is exactly 12, this might be 16.00003. something like that, right? It can't be exactly 16. Well, I guess it could, but they never are. They're always fractionals. When you actually determine the atomic mass unit for the isotope, carbon is the only one that's 12 to infinite number of zeros. That's because we picked it that way. Okay, so that's for the individual isotopes. But as chemists, we don't want to have to deal with individual isotopes. We want to deal with the naturally occurring abundance of isotopes in our elements. So if we collect carbon from the environment, the people who do this for a living have determined that the abundance of carbon-12 is about 99%. And the abundance of carbon-13 is about 1.11%. And carbon-14 doesn't matter because it's so small and it's radioactive anyway. So we're just going to use the top two to calculate an average atomic mass for the atom. It's kind of like calculating your grade point average, right? You're taking a course that's worth 4 hours and say you get a B in it. So that's worth a certain amount. But if you take a course that's only got 2 hours and you get the same B, it's worth less to your average. Okay? All right. So this is a weighted average. What we do is find out what's the contribution of 12 to the overall, and what's the contribution of 13 to the overall. You multiply the values by a fractional equivalent of the percent. So it'd be 0.9889 times 12 would be its contribution. Let me see if I've got that. Yeah, there it is. And 0.0111 times 13.0034. Notice that that's not 13, right? Because it was originally compared to 12. So once you multiply those out and get a value for each one, add them together, that's going to be, as soon as I get to it, 12.01 atomic mass units for the average mass of a naturally occurring carbon atom. It could be a 12, it could be a 13, doesn't matter. The average mass is what's important to us. That way, we don't have to bother with isotopes when we're doing our chemistry. Okay. I already said that. So this is just, I'm not going to spend a lot of time here because we don't have a lot of time. But this is a schematic of a mass spectrometer. It just shows you one way that people who do this for a living isolate the individual isotopes. Okay, first they have to charge the atoms, right? So in this case, they would take carbon-12 and knock an electron off of it. And then carbon-13 and knock an electron off of it. You have to do that, otherwise you can't accelerate them through an electric field. So that's what we're doing here. We're accelerating through an electric field, then it's going through a magnetic field, and the same, since they have the same charge, the same force is being applied to both ions. But the one that's heavier bends the least. Right? It takes more force to bend a heavier atom than it does a lighter atom. So the lighter atoms end up over here, and the heavier atoms end up over here. And we've got electronic detectors now that will count individual strikes, which is assumed to be an individual ion as it strikes the detector. And they can count them all. And if you're set up properly and position your catcher in the right place, you can catch those individual ions and isolate them. And they probably have dedicated mass spectrometers to do that. They have some for analysis and some for, let's see, what would that be? Segregation. Segregating the isotopes. Come on. There we go. Okay. So let's take this element that has 62.6% of an isotope that weighs 186.956 atomic mass units. Notice they use just a U. I think I should change it in the slide. I use AMU because it's less likely to be mistaken for something else, right? Little u, you might think it's uranium. And the other isotope at about half the abundance is 184.953 atomic mass units. So what's the average atomic mass for that? Do the same thing we did with carbon. Convert to the fractional, multiply by each value, and add the results together. Okay? And that should give you 186.2 atomic mass units, average mass for that element. Then identify the element. Okay, we know how to identify elements easily if we know the atomic number, right? The Z number, that's the number of protons. But I don't know if you find it strange or not, but if you know the atomic mass of your element, you can probably find it on the chart, because as the atomic numbers go up, the masses go up too. So you just look at the masses until you find one that's very close to that and very far away from its neighbors, and you're probably right on it. And if we do that, we find that it's, there it is, rhenium. You didn't have to memorize that. Rhenium is right there. It's a transition element. Okay. Okay, here's the next problem. We don't do chemistry in atomic mass units. We do chemistry in grams. So, as it turns out, those atomic mass units for this isotope, 12 on out, atomic mass units, is also can have the units 12 grams per mole of mole of atoms. So what is a mole? Mole is just a number. I mean, it's related to a real determination, but we don't have to worry about that right now. A mole is 6.022 times 10 to the 23rd things. Could be atoms, could be ions, could be molecules, could be chickens. It's still just a number. So if you have that many atoms of this isotope, it will weigh exactly 12 grams. Okay, that's something we can use because it's got mass that we measure on the balance. So that's our connection to the number of atoms and what's their mass. Okay, the number of iron atoms in 4.48 mole sample of iron, right? That's a unit conversion. You just say 4.48 moles, right? And that's abbreviation. MOL is abbreviation for anything. MOLE is where you write it out. It makes a lot of sense, right? So if you convert that, you just need moles on the bottom and atoms on the top, right? You know your conversion factor. Right? Then you multiply it out. There it is. 2.70 times 10 to the 24th atoms. That was 3 significant figures. The answer has 3 significant figures. That's just an exercise. We normally don't work in atoms. So this method of conversion is just to reinforce the fact that that's what the mole means. But when we start actually doing stoichiometry, we're going to use mass per mole and just forget about the atoms. We only need, since mole is counting, atoms counting, mole is more convenient. So we'll use mole instead. So when you look at the periodic table, those numbers in that periodic table in the upper left-hand corner, those could either mean that many atomic mass units for the average atom of that element, and it could also mean that many grams for a mole of those atoms. So the molar mass of nitrogen is 14.01. And for our purposes, 2 decimal points is fine. In fact, year after year, decade after decade, those numbers don't change from in the 2nd decimal point. They only change in like the 5th or the 6th decimal point as they refine their numbers. So we don't have to worry about it. As long as we stay with 2 decimal points, then we can use a periodic table that's 50 years old. So what's the molar mass of a compound? If the molar mass of the element is 14.01, what's the mass of a compound? All you have to do is add up the molar mass of each of the elements times how many there are in the compound. So we have I would have written 1.01 for hydrogen. 2 times that, because you have 2 of them. When you have a mole of the compound, how many moles of hydrogen are you talking about? 2. So it's 2 times 1.01, and then 1 times 16. And that molar mass of water is 18.02 grams per mole. And you can do that for any compound. You just have to be careful about counting the number of atoms in the formula. And of course, before that, you got to write the formula correctly. That helps. Like this one, barium nitrate. So you look up barium, it's way down there, right here. Barium's 137.33 grams per mole. We left the per mole out just for convenience. And how many nitrogens do you have? Well, that nitrate has a subscript. So you got 2 nitrates, which means you have 2 nitrogens and 6 oxygens. Okay. And you can't see it too well on that screen. So you got to be careful with these parentheses and be sure that you're counting all the atoms that are in there. And then add them all up, and that's a big formula, 261 grams per mole. If you have 6.022 times 10 to the 23rd of that unit, barium nitrate, it will weigh 261 grams. Okay, this is kind of a dumb slide. What would be the closest average mass of one atom of copper? It wouldn't be A, B, C, or D, right? No atom weighs a gram. So process of elimination is the last one. Come on. There we go. There's the calculation. If you want to actually do it. And it's just dimensional analysis. Come on, there we go. How about the number of copper atoms in a 63.55 gram sample of copper? That's a trick question. Don't immediately go to dimensional analysis because, excuse me, a tickle. Because 1 mole of copper atoms weighs 63.55 grams. Right? Get that off the periodic table. So how many atoms is that? Avogadro's number. Okay? Now, suppose you have a 100-gram sample of each one of these elements: magnesium, zinc, and silver. Okay, we got 100 grams of each. The question is, which one has the greatest number of atoms? How many atoms does it take to make 100 grams? Well, we could calculate it, but we're just comparing these three and putting them in order, or which one's the greatest. So how many atoms would it be? Well, we'd need the molar mass to do the calculation, right? So we might as well get the molar mass off the periodic table. 24.31 for magnesium grams per mole. Zinc. Got to be an easier way to do this. A periodic table. Oh, I got one right over here. There we go. So zinc, right? Zinc is 65.38. And silver is heavier, I bet, 107.87. Grams per mole. Okay, which one would have the greatest number of atoms? How many atoms of silver would it take to make 100 grams? Right, if we had grams per mole.
Magnesium.
Yeah. So actually, this needs to be flipped to do 100 grams. Right. Yeah, magnesium would have the greatest number of atoms because it takes more of them to add up to 100 grams. Okay, it takes fewer of the silvers. These would be the least. Because each atom weighs so much, it takes fewer of them to make 100 grams. And then zinc would be in the middle. Yep. Okay. How about ranking these as from greatest to least number of atoms? All right, so we got silver, zinc, and magnesium. They switched them around on us. Let me just write it all over again. Silver, zinc, magnesium. Okay, but we got different amounts, 107.9 grams. And zinc, 70 grams. And magnesium, 21 grams. Okay. So the simplest way to approach this is to say, is that equal to a mole, greater than a mole, or less than a mole? So if we look at their molar masses, silver would be, that would be exactly a mole. Okay. Zinc, 70. That's greater than a mole. And magnesium, well, we know it's 24, so it's less than a mole. Now you can put them in order. Numbers of atoms, right, from greatest to least. So the greatest would be greater than the mole, zinc, and then silver, and then magnesium. Okay, so we've compared different masses simply by comparing them to how many moles there are. How about this one? Do I have that done on the slide? I don't have to write it. That eats up a lot of time when I have to do that. No, it didn't. Okay, I'm going to write this one up here because it describes a procedure that I call Henry Ford. It's an assembly line procedure, which means you do the same thing. If I were a worker on an assembly line, I do the same job the same way all day long. So we're going to take each one of these 100-gram samples and treat them the same way and get an answer here that we can compare. So if we've got water, dinitrogen monoxide, laughing gas, that's nitrous oxide, C3H6O2, which is probably propionic acid. It's a fatty acid. And carbon dioxide. Okay. You got 100-gram samples of each one. Right? 4? Yeah. All right. So what do we need to convert these to answer the question? Rank them from greatest to least numbers of oxygen atoms. So if we're going to do oxygen atoms, first we got to find out how many moles of compound do we have? Say if we had 1 mole of water, how many moles of oxygen would you have? 1. If you had 1 mole of this one, how many moles of oxygen? 2. Right? 1 formula unit here gives you 2 moles of oxygen, 6 moles of hydrogen, and 3 moles of carbon. Okay? All right, so to convert them, what do we need to know? Here's my assembly line. Grams on the bottom, moles on the top. Whenever you see moles and grams in a quotient, think molar mass. So what's the molar mass of oxygen, water? We did that one before. 18.02. Dinitrogen monoxide. Nitrogen's 14.01, so times 2 is 28.02 plus 16. Can anybody do that in your head? 16 plus 28.02. 4402. 44.02. This one. Okay, we need 3 carbons, 12.01. All right. 6 hydrogens, 6.06, right? 6 times 101. And oxygen. 1 oxygen, 16, 2 oxygens is 32. Rounded to 2 decimal places. So that's 7409. Okay. Carbon dioxide. That's 32 for oxygen, 12.01 for carbon. Oops. Yeah, that's right. 4401. Okay. So that gives us the number of moles of the compound. Right? Now that we know how many moles of compound, we need a conversion factor that will convert that to the number of moles of oxygen. So we need the compound on the bottom and oxygen on the top. Okay, so the number here is 1. For every 1 compound, you have 1 oxygen. How about this one? Same thing. This one's got 2 oxygens for every 1 compound. This one has 2 oxygens for every 1 compound. Okay. That's the hard part. That's the thinking part. The rest is number crunching. Okay. So do we need to do that? You just divide 1802 into that times 1. 4402 into that times 1. 7409 into that times 2. 4401 times that times 2. And you get numbers. Yeah, maybe I better. Let's be complete. All right. So 100, 18.02 times 1 is 5.55. That's moles of oxygen. And 100 divided by 44.02 times 1 is 2.27. Okay. And 100 divided by 7409 is 1.35. And carbon dioxide, 100 divided by 44.01 times 2, 4.54. There we go. So, from greatest to least, greatest is water. That's number 1. The next one is carbon dioxide. The next one is laughing gas. And the last one is our fatty acid. Okay. So that's my Henry Ford procedure. We did exactly the same calculation all the way through. The only thing that changed were these that were specific for the compounds, these values and these values. But the calculation is exactly the same with those changes. Okay, this is an idea about problem solving. You can boil it down into 3 steps. What's the question? How are you going to answer the question? Is there enough information in the word problem to answer it, or do you need to go outside and get some more information, like go to a periodic table? Or do you have to have a formula memorized or know where it is in useful information? And then you map out your plan. How are you going to get there? And do the calculations. Sometimes it's just simple. Bam, you got it, 1 step. Sometimes you have to break it into small pieces and work those answers, separate answers together to get you the final answer. And then do a reality check. Does the answer make sense? I mean, if the answer is going to be how many grams of carbon in a leaf sample, and your answer comes out 34 billion kilograms, you might want to step back and say, I made a mistake somewhere. Reality check. Okay. When bench chemists analyze a compound, they got to make sure the compound is pure first, of course. But once they've purified the compound, then they want to know what the elemental composition is. And it's common to determine the mass percent of each element in the compound. So you run it through your procedure, and you say it's 12% carbon and 25% hydrogen, and whatever's left over is oxygen, just for an example. That mass percent is a starting point. If you want to know anything else about the compound, you've got to do some calculations. But for the bench chemist in a lab, that's where you start. You can also calculate the theoretical percent composition by mass of a known formula. And here's how you do it. For iron 3 oxide, Fe2O3, what's the mass percent of iron? Well, you have to assume that you've got a mole of the compound, right? If you have a mole of the compound, then you've got 2 moles of iron. So that's why we multiply 2 times 55.85. That's the molar mass of iron. And that's ratioed to the entire molar mass of the compound. So you have to have iron in there also, plus whatever's left over. That's why we have 2 irons in the numerator and the denominator. In the denominator, you add 3 oxygens. That's the ratio of iron to the compound. Then times 100 is percent. Okay? So if we were to take that compound and go to the bench and analyze it and get percent values, they should be close to that. It should be close to about 70% iron. You could, experimental error could be, 69.2. That can happen. But that's theoretical. Okay. We don't have time to go into that one too much. From these same compounds, rank them from highest to lowest percent oxygen by mass. You would just go in and calculate, using that formula, how much oxygen is in water by percent, nitrous oxide, propionic acid, and carbon dioxide. Use that same formula and just compare the values. And as it turns out, the highest percent oxygen is water. That should make sense, right? Water is 16. Water is 18. Oxygen is 16. So it's almost all of the molecule is oxygen. All right. So now we want to use that percent composition to figure out what's the formula of our compound. Say we don't know it's Fe2O3, or in this case, we don't know what it is. Carbon and hydrogen are the two elements. You can use percent composition by mass to determine first the empirical formula. The empirical formula is the simplest whole number ratio of the number of atoms of each element in a compound. Right? So we would say, what's the empirical formula for this one? Okay. You can divide both of them by 6 and get a simpler ratio, right? So it's 6 to 6 or 1 to 1. How about this one? That's probably benzene, and this is probably acetylene, right? Same stuff you blow in a torch. It has exactly the same empirical formula, simplest whole number ratio. So if we want to go from here, because if we do this, we don't know which is right. We want to get to the molecular form. So if we want to go from here to here, what do we need? We need a multiplier. We need to know, what can we multiply by these 1 and 1 to give us that? Or maybe it's this one to give us that. So in this case, X would be 6. In this case, Y would be 2. So that's where we're headed. First, we're going to find out what's the empirical formula from the percent composition. And then we're going to use one other piece of information, the true molar mass of the compound, to make the step from empirical to molecular. Okay, just heads up, that's where we're headed. I'm not going to wait here. This is a analytical chain. If your compound is carbon, oxygen, hydrogen only, you can use this. I've used one of these before. You burn your sample in pure oxygen, which means you can't do a direct analysis for oxygen because you flooded the system with it. But you can catch water, which tells you how much hydrogen is there, and you can catch carbon dioxide, which tells you how much carbon is there. And you can weigh before and after each one of these devices. And then you make the equivalence from carbon dioxide to pure carbon and water to pure hydrogen. And then if you know by qualitative analysis that it's only carbon, hydrogen, oxygen, then you can get the oxygen by difference. Okay, it's whatever's left over. Okay. So suppose we have a compound that's made up of carbon, hydrogen, and oxygen with these compositions. All right, so let's put this one on the board. Carbon, hydrogen, oxygen. Composition is 49.3% carbon, 6.9% hydrogen. Remember, this is mass percent. It's grams per 100 gram sample. And 43.8. Okay. So what are we looking for? We're not looking for the ratio of masses, right? If we want the formula, we've got to ratio numbers of atoms in that compound. So we're looking for moles. How many moles does that represent? Well, at this point, we're stuck because percent is a dimensionless number. It doesn't mean anything. So if this is parts per 100 and it's mass percent, then this means it's 49.3 grams per 100 gram sample, right? So we can substitute here grams. If we assume 100 gram sample. Okay, now we can work with it. The mass ratio is still the same as the percent ratio, right? The law of definite proportions. All right, so we want to convert these into moles of each one so we can compare the numbers of atoms. All right, so Henry Ford's on the way again. All right, get rid of grams, leave us with moles. All right, what did I say about that quotient? Molar mass of each one. So 1 mole of carbon weighs, you don't remember? Right. Okay. How about hydrogen?
1.01.
Yep. And oxygen? Rounded off to 2.
15 point. So it's 15.99.
Yeah. Yep. 16. Okay. So if we divide that into each one, then we should be able to find out what's the mole ratio of each element in the compound. All right. So let's do that. Quick, fast, and in a hurry. 4.10. That's moles of carbon. That's it. 6.9 divided by 1.01 is 6.83. Moles of hydrogen. And the last one, 43.8 divided by 16 is 2.74. Oxygen. Okay, we can't write a formula with that, right? Because the formula implies that it's whole number atoms. We don't need fractional atoms. But the ratio is correct. That's fixed, right? Law of definite proportions. So how do we get them to whole numbers? Well, if the ratio is fixed, if we multiply or divide each one of those by exactly the same number, then we haven't changed the ratio. That's a math rule. Well, let's divide by the smallest one. Okay, now what do we have? That's obviously 1. How about this one? 683 divided by 274. That's about 2.5. Now we're starting to estimate a little closer because of experimental error. We have to sort of take liberties. The actual number is 2.49559. That's close enough to 2.5 to get us to whole number status. And then 4.1 divided by 2.74. And that's about 1.5. I should do this. Well, that's exact. Okay. So now we're getting closer. How do we get rid of those halves? Well, we'll give you a whole number if this is where you're starting. How can you get a whole number out of that? Multiply by 2. And you get rid of this, because 1/2 is that right there. Right? So if we multiply that by 2, times 2, times 2, times 2, this gives you 3, that gives you 5, and that gives you 2. Okay, so the empirical formula, the ratio, is 3, 5, and 2. That's the empirical formula. Now we want to go to the molecular formula. We want to know, what is this multiplier? Well, we're given another piece of information. The molar mass of the compound is 146 grams per mole. Right? So if we find out what that number is, that gives us a compound, and we know what the mass of that compound is per mole. So what's the ratio of the mass of this compound to that compound? Well, you divide this mass by that mass, right? I call it the empirical mass. So the empirical mass of this one is, let's see, carbon is 12.01 times 3, and then hydrogen is 5.05, and oxygen is 32, because they're 2 times 16. That's 7308. So this one is 73.08 grams per mole of that formula. So what would this have to be to give us that value, 146? It won't be 1. 1 just leaves us where we are. What about 2? I think 2 is pretty close. If X is 2, then you get this value out of it. So that means this one is C6H10O4, 2 times. Okay? And that's the same procedure we use for any problem solving where we want to go from percent by mass to the molecular formula. You need the percent by mass, but you also need the true molar mass of the compound. If you don't have that, then you're stuck at empirical. All right. Let's see. Chemical reactions. I'm going to run out of time. Okay, here's what I'm going to do. If you can't stay, I'm going to stay until I'm done. So if you can't stay and you have to go, then the video would be on Brightspace. Okay. I'm sure we can get through 3, but I'm going to jump into 4 because next week we do a review. So we have to get through it today by some form or fashion. Let me try this thing. That's better. All right. So when we write a chemical reaction, we put the reactants on the left-hand side and products on the right-hand side and put an arrow in between them. We don't use an equal sign because equal implies something else. What we're saying is that those reactants come together in some chemical form and they produce the products. Now, later on, we're going to see that that arrow can go both ways. But for now, we're only sending it one way. Okay, in this case, the equation is balanced. And what do we mean by balanced? Well, in Lavoisier's day, a balanced equation was the mass of your reactants equals the mass of your products. But now that we know about atoms and molecules, the reason that Lavoisier's law of conservation of mass works is because you have the same number of atoms on the reactant side as you do on the product side for each of the elements. Right? So you have 2 carbons, you look over there, 2 CO2s, that's 2 carbons. And those numbers that are in front of the compounds are called coefficients. They tell you how many moles of each of those, whether it's O2 or ethanol, that's the drinking stuff. Reacted with oxygen makes CO2 and water. That's what happens in your body when you drink alcohol. Your body turns it into carbon dioxide and water. Or you can burn it. Right? It goes faster that way. So, 6 oxygens, and you look on the right-hand side, there are 4 oxygens in carbon dioxide and 3 in, let's see, 4, oh no, there's 7 oxygens. You have 3 from oxygen and 1 from ethanol. So you have 7 on the left and 7 on the right. That equation is balanced. Now, one unbreakable rule is that when you balance an equation, say we started off with no coefficients, you would know pretty quick that that's not balanced. The only way that you can balance an equation after you've written the reactants and products correctly is with coefficients. You can't touch the subscripts. Okay, just a caveat. When we put that there, reactants, products, this is overall. These reactants overall become those products. But inside here, it's very busy. There's lots of stuff going on, right? We're only worried at this point about what comes out the end. It's kind of like a black box. Okay, so these are the written procedures for balancing an equation. Most textbooks, I'm not sure about yours, I haven't looked at it in a while. Most chemistry textbooks say then you balance your equation by inspection, which is a cop-out. It doesn't tell you anything about the reality of balancing an equation. So I'm going to show you how to do that. And that document, helpful hints, I've got it in the slide set, but I've also got a Word document, PDF document in Brightspace in this module that combines all of those helpful hints. Okay, so here's helpful hints 1, 2, and 3, and then 4. Let's see, come on, 5 and 6. And let's go through an example. All right, this is going to be the helpful hint where you have polyatomic ions. If you have a polyatomic ion in your reactants and you got the same polyatomic ion in the products, it's not broken up in the process, it just simply swaps partners, then you can keep that polyatomic ion as a balancing unit. You don't have to break it up. All right, so here's my method. I call it my budget method. You inventory each one of the balancing units in your equation. Ammonia, ammonia's there, ammonia's here. Phosphate's there, phosphate's there. Calcium is there, calcium is here. Chloride is there, chloride is there. So you've accounted for everything that goes into the reaction and makes products. Then you inventory them. This is an unbalanced equation. So you say, these compounds are written correctly. That's the first rule. Then you inventory them. So initially, you're going to have 3 ammonias, 1 phosphate, 1 calcium, and 2 chlorines. That's on the reactant side. On the product side, you have 1 ammonia. Come on. 2 phosphates, 3 calcium, and 1 chlorine. I think my battery's getting weak. And you can see right off that this is not balanced. Right? 3 ammonias on one side, 1 on the other. 1 and 2, 1 and 3, 2 and 1. You know it's not balanced, which means if you keep, as you insert coefficients and you recalculate, then you will know instantly whether you have arrived at a balanced equation. Right? So the next question is, where do we start? Right? Well, one of my rules, helpful hints, is if you have an element in there with no other elements with it, like you may have O2 or H2 or whatever the case may be, leave that one to last. Because if you put a coefficient in front of the element, that's the only one you're changing. But if you put a coefficient in front of any one of these, you're not just changing the one you're targeted, but you're changing whatever else is in the compound. So save the elements to last. Okay? Now, where do we start? Well, let's see. They're all different. So we can either start with ammonia, we can start with calcium. I think the way I set this one up, it starts with calcium. But it doesn't matter where you start. Sometimes with experience, you'll start where you'll get to the end quicker. But eventually, no matter where you start, you'll end up with a balanced equation. Except under one condition. You wrote your compounds wrong. If you wrote the compounds wrong, it will never balance. Okay? Just a word of warning. So be sure that you've written your reactants products correctly. All right. So we're going to do, there we go. We're going to do calcium first. If we put a 3 in front of calcium chloride, that means we have to change the calcium to 3. We also have to change the chloride to 6. Okay. Now we got the calciums balanced, but we changed the chlorides. So let's go over to the product side and correct that. Put a coefficient in front of ammonium chloride and correct the chloride. So the coefficient would be 6. Right? 6 in front of ammonium chloride would give you 6 chlorides on the product side. But it would also change the ammoniums to 6. So we got to fix that. Come on. I'm going to have to go up here. There we go. Now what do we have left? Well, you can see from the budget that what we have left is ammonium on the reactant side and phosphate on the reactant side. So if we want 6 ammonias on the reactant side, what's the coefficient? Yep. Okay, the 2 will get us 6 ammonias. That balances the ammonias. And the phosphates now are 2. And we're balanced. You can see from the budget right off that you don't have to go any further. Okay? Now, one rule that we're going to stick with for the time being is that your coefficients should be the simplest whole numbers. You can't divide them by the same number and get a simpler ratio. Right? In this case, we can't. 2, 3, don't forget 1. That's understood 1. 2, 3, 1, and 6. We can't simplify it any further. But sometimes, in this next slide, if we balance calcium oxide plus carbon yields calcium carbide plus carbon dioxide, If we balance that one, then the simplest ratio will be 2, 5, 2, and 1. But the ratio would also be valid for 1, 2.5, 1.5. But that's not whole numbers. We don't use fractional numbers unless we have to. Now, later on, let's see, it's probably in the second semester, we'll use fractions when we start talking about electrochemistry and the heats of formation, right? So don't worry about that right now. Right now, we go for the simplest whole number. And that would also work. But you want the simplest whole number ratio, and the first one that we outlined was it. Okay. So which of these are true? The number of molecules is conserved. Do you have the same number of molecules on the reactant side as the product side? Not necessarily. If you do, it's purely accidental. So 1 is false. The coefficients tell you how much mass of each substance you have. True? No. Tells you how many moles of each substance you have. Doesn't say anything about the mass. Atoms are neither created nor destroyed. That's true. That's still true. It was true for John Dalton, and it's true for us. The coefficients indicate the mass ratios of substances. That's another way of saying Roman numeral 2, which is false. We're not talking about mass ratios here. We're talking about number ratios, mole ratios. The sum of the coefficients on the reactant side equals the sum of coefficients on the product side. Nope, not necessarily. If they do, it's purely accidental. The coefficients are there to make sure that the same number of atoms of each element on the reactant side equals the number of elements of each, number of atoms of each element on the product side. Right? So that's the only true one in the bunch. This is just a reminder. Subscripts can't be touched. Once you get the proper formulas for your compounds or elements in the equation, then you can't touch the subscripts. And most reactions, you'll be given the reactants and the products, because the conditions for a reaction will favor one reaction over another. And you can put two products together and get reactants, you can put two reactants together and get wildly different products depending on the reaction conditions. So most of the time, you'll be given both the reactants and the products. You don't have to figure that out. One exception, and that comes in chapter 4. When we put two soluble ionic compounds together, we have one ionic compound in solution here, one in aqueous solution here, put them together. Then you can figure those out, what's going to be your products. Okay? So you will need to be able to do it then, and it's really not that big a deal. All right. So stoichiometric calculations. If we want, and here we're talking about mass. If you put together a certain mass of one product reactant and a certain mass of another reactant, we want to find out how much product will you get, right? And we already know that the reaction equation is not built that way. But that doesn't mean we're stuck. We can still use it. And I'm going to show you how. All right, those are the steps. And they're there just for the slideshow. So we're going to go through it in a minute. Okay, there's a flow chart in case you like those. All right, how about this one? Consider the following reaction. P4, let's see. P4, I'm going to leave off the phases because they're not necessary for balancing. And this equation should be balanced already. We can check it. 10 oxygens, yep, 10 oxygens. 4 phosphorus, 4 phosphorus. Okay, so it's already balanced for us. If we say 6.25 grams of phosphorus is burned in oxygen, how many grams of oxygen are required to convert all of that into this? Okay, sounds like a big job, but not really. The rule that you have to remember is you can't go anywhere in this equation unless you got moles. Grams will not take you anywhere in this equation. So we got to find out how many moles that is. Then we can move in the equation. Like we can move from here to here. Only moles can get past those barriers. So how do we find the number of moles of P4? Well, we got 6.25 grams. Dimensional analysis. Cancel the grams, leave us with moles, correct? So we need to know the molar mass of P4. So we look it up. Phosphorus is 30.97 times 4, 123.88. There we go. So we divide that into 6.25, and we get 5.05 times 10 to the minus 2. What? Moles of P4. That's how many moles of P4. Now that we got moles, we can move. The question is, how do you get from here to here? The ratio of this reaction tells us that for every mole of P4, you need 5 moles of oxygen. That's your conversion factor. If we've got this many moles of P4, the ratio is 1 of those or 5 of those. Okay? So multiply 5 times that. And I get 2.52 times 10 to the minus 1. Moles of oxygen. Okay? The question though is, what's the mass? So how do you get mass out of that? Same as always. Molar mass. So what's the molar mass of O? Oh, O2, excuse me. 32 grams per mole. Okay. So 32 times that value is 8.07. That's how much oxygen is required to consume all of that P4 and make this compound. Okay? There it is. Okay. It would be nice if we had time to do this one, but we don't. What you need to do is first write the compounds correctly. Methane reacts with oxygen, right? Methane is CH4. That's why I would give it to you, because we haven't talked about organic compounds. Reacts with oxygen. Oxygen in the air is O2. It's one of those diatomic elements, just like hydrogen, nitrogen, fluorine, chlorine, iodine. They're all diatomic. So when the word problem says react with oxygen, react with nitrogen, or react with fluorine, remember, it's always a subscript of 2. Right? That's the first point that you could trip. And then produces carbon dioxide and water. So the equation now is balanced. And we could use our budget method and do it. A side-by-side reaction, not the same reaction, but it occurs in a different vessel, is ammonia plus oxygen makes nitrogen monoxide and water. Okay, and that one's balanced. Okay, once we've done that, now we're gonna ask the question: what amount of ammonia would produce the same amount of water as 1 gram of methane? So how would you approach this problem? Okay, well, if they're going to produce the same amount of water, don't you need to know how much water is being produced by the one that you're given? You got 1 gram of ammonia, so you need to know the moles. Methane. 1 gram of methane is 6.23 times 10 to the minus 2 moles of methane. Right? You got to get moles or you can't move. So now that we have that many moles, we're going to convert to moles of water using our coefficients as conversion factor. For every 2 waters, you need 1 methane. Okay, so we have that many moles of water. Well, we want to know how much ammonia would produce exactly that same amount of water. So we're going to say that many moles of water would produce how many moles of ammonia? So there you have the number of moles of water. Let me see if I can do it this way, can I? Yeah. That much water will produce how much ammonia? 6.23 times 10 to the minus 2 moles of ammonia. Then convert back to grams, you just need the molar mass of ammonia. And now we know that 1.12 grams of ammonia will produce exactly the same amount of water as 1 gram of methane. Okay, did I lose anybody? Or are we boring you? If you're bored, that's good. Okay. All right. Up to this point, we've had reaction equations, balanced equations, and we sort of let it slide. But these are theoretical. In other words, we're assuming that all of this is converted to a certain amount of that. And in this case, oxygen is in excess. We wanted to know how much oxygen was required, but we didn't say that there was a limit to how much oxygen. So it's in excess. That makes this one limiting. What that means is the limiting reactant is the one that runs out first. When it runs out, the reaction stops. Doesn't matter how much of the other one you got. Once you run out of this one, it's all over. No more. So when you're presented with a problem like this, you have to figure out, is one of the reactants unlimited? Is it excess? That's good. Then you can use up all of the other one and go ahead on. But if you're given values, masses or moles of each reactant, say we're given something here, we're given something there, then you've got to decide which one is limiting, because that's the one that will stop the reaction. Okay, so we need to figure a way to do that. This is an artist's rendition. In this reaction, nitrogen and hydrogen make ammonia. This is a stoichiometric mixture, which simply means that you've got just exactly the right number of molecules of H2 to react with just the right number of nitrogens to make ammonia. There are no leftovers. That never happens. This is purely theoretical. In the lab, when you're measuring out these reactants, there's always error, and one of them is going to be limiting. So the stoichiometric mixture is a starting point, and you move to the excess or limiting from there. This is an example of limiting. Which one is the limiting reactant? Well, the one that's used up, because if you got excess in one, then the other one is the limiting one. and we have excess of nitrogen. Notice that there are 2 molecules of nitrogen up here, right here. They got no dance partners. And they're still over here in the product side. Those are excess, which means that hydrogen has to be limiting. Okay. All right. I'm going to spend just a few seconds on this one. This balanced equation, 2 hydrogens plus 1 oxygen makes 2 waters. If you have 2 moles of hydrogen and 2 moles of oxygen, how many moles of water do you make? Well, which one's going to run out? Hydrogen's going to run out because you got twice as much oxygen as you need. You only need 1 mole of oxygen. So when 2 moles of hydrogen run out, how many moles of water do you have? 2 moles, because the ratio is 2 to 2. 2 moles of hydrogen and 3 moles of oxygen. You're in the same boat. You're still going to run out of hydrogen. So that makes 2 moles of water. 2 moles of hydrogen and 1 mole of oxygen. That's a stoichiometric mixture, right? 2, 1, 2. 3 moles of hydrogen and 1 mole of oxygen. Now, which one runs out? Oxygen runs out because you only need 2 moles of hydrogen. You got 1 left over when the reaction's done. But they all make the same amount, 2 moles of water. Okay? Okay. I'm going to skip that. Now, there's another fly in the ointment. When you go into the lab to conduct a reaction, maybe you measured out the reactants wrong. There's error there. Or when you're recovering product from the mixture, it's not 100% recovery. So the actual amount, the actual yield of a product is a certain number of grams. But the theoretical yield is based upon the equation itself, right? If I say this many grams of that, then if I use all of them up, it would make a certain amount of this. But if I actually measured that amount of P2O5, it will probably be less than the theoretical amount. So if you ratio those two together, actual divided by theoretical times 100, you get a % yield. And that's the way it always works. Sometimes you get high yield, sometimes you get low yield. The Haber-Bosch process where you take nitrogen from the atmosphere and combine it with hydrogen. To make ammonia, right? So if we put, and then that's good. That's balanced. This reaction can run in reverse, and we'll find out later why. But the efficiency here was very low. It was way, way, way less than 1%. Right? So Haber decided, well, if I heat it up, that'll give it more energy to make the reaction go. The trouble is, as you heat it up, the reactant side is favored. Right? So he stuck in a catalyst, finely divided iron. And that caused the reaction to speed up toward this direction. And he would take this gas and that gas to make this gas. Well, the condensation point, the melting point, the vaporization point of this one is at a much higher temperature. So all you have to do is cool it down a little bit. This would drop out as a liquid, and these would stay gas. And you just run them back through and run them through the reaction again. And after you do that about 4 or 5 times, you get up to 15% efficiency, actual yield over theoretical yield. That was a practical example, but it was good enough to make the process economically viable. Now, Hopper was active around the time World War II started, World War I. And the Allies were boycotting Germany from getting nitrates from Chile, like bird guano. So they had to figure another way to get their nitrogen, and they did it this way. They made ammonia, then all you have to do is oxidize the ammonia, makes nitrates, now you can make gunpowder. Or they probably used cordite then. Anyway, that's percent yield. Now this last problem, I'd like to do this in complete, but we're running out of time. What we need to do, I'll sort of gloss over 4PF3. All right, so what mass of P4 is needed to produce exactly 85 grams of that product if you know that the efficiency is 64.9%. Okay, what you have to do, since this is theoretical, you got to find out what is the theoretical amount of this that would be produced. And that's where this comes in. Right? So you would take that, that's the actual amount. Right? And you need actual and theoretical on top. So it's flipped. So the actual would be 0.649, and this would be 1. So you divide 0.649 into 85, and anybody who knows anything about math, if you divide a number by a fraction of 1, the answer is bigger than the original, right? You divide by this fraction, and you come out with a bigger number. Now you can take that number of grams and convert it into moles, use the ratio of 4:1, find out how many moles of this, convert it back to grams, and that's your answer. Okay? There should be examples of that in your review documents. So you got a whole week to work on them. Oh, they're the calculations. Okay? 130.97 grams theoretical PF3. Convert that to convert that to moles, and then convert the moles of PF3 to moles of P4, then convert those back to grams. So you need 46.1 grams of P4 to guarantee 85 grams of product with that efficiency. Okay. So let's go to, let's see, 4. All right. I'm still shared. That's good. Slideshow. There we go. Now we're going to talk about types of chemical reactions. Does anybody need a break? Yeah, go ahead. Let me see. Put this on the charger. Let's put this in here. Yep. Put a charge on it. Types of chemical reactions. All right, when we put things in solution, sometimes that's the best way to make all the reactants available is to have them in solution. If they're solids, then they can only react at the surface of the particles. So if you're going to do that, then you have to divide the particles way down to really small particles. That's why in a coal mine, coal dust explosions are a real hazard because the coal is a hydrocarbon that can be easily burned. But if you mix it with oxygen and the particles are very small, you have lots of surface area, then what would normally burn slowly in your furnace is a chunk of coal now burns really fast and can burn so fast it makes an explosion. But if we put things in solution, then what we need is a good solvent. And a large part of the time, a good solvent is water. And you've probably heard this, the Earth is a water planet, right? What is it? 2/3 of the surface of the Earth is covered in water. It can dissolve many substances. It's been referred to by some as the universal solvent. It's not really universal. There's some things that water will not dissolve or will dissolve in such small amounts it's not significant. And we're going to talk about why that is. It has to do with the polarity of the molecule. When we talk about poles of a molecule, think about magnets, right? If you have a magnet, you got a north pole and a south pole, right? Well, you don't have magnetism like that in a molecule, but you do have electrostatic charge, redistribution of electrons, so that you have one end is maybe more positive than the other, right? And water is like this. Okay? We're going to talk about electronegativity later, but at this point, just know that this is a covalent bond. Why? Because that's a nonmetal and that's a nonmetal. So it has to be sharing electrons, but they don't share equally. Oxygen is more strongly attractive toward electrons than hydrogen is. So we get a slight redistribution that way. I put a plus on this end to show this is the plus end, and that's the negative end. Okay, that's called the dipole. So this is going to be slightly negative, and that Greek letter D, delta, is what we use for slight charge. It's not a complete charge. It's not like making an ion, where you have complete transfer of electrons. This is a slight negative charge. And this is going to be a slight positive charge, and this will be a slight positive charge. And then overall, actually this needs to be 2. Overall, the molecule is going to be polar in that direction. So this side of the molecule is more negative than this side. Okay, what does that mean? Well, in pure water, that means that the water molecules are going to align so that they're like that. Since this is negative and that's positive, you're going to get an electrostatic attraction. And that's why water at room temperature is liquid. If it weren't that way, I mean, if the hydrogens were out like this, then those two opposing dipoles would cancel each other out, and water would be a nonpolar molecule. And at these temperatures, water would be a gas, and we'd be in big trouble. Okay, but the polarity of the molecule is what makes it so good at dissolving some substances. Ionic compounds, a lot of them are soluble in water because it's polar, right? They have, when they go into water, they break up into positive and negative ions, and they associate with water however the opposite charges do. Let's see if this has got any sound with it. Okay, I'll tell you what I'm going to do. You can see this here and it looks great. I'm going to look at the recording and see if it came through okay. If it did, I'll leave it alone. But if it didn't, I might modify it. Maybe I'll boost the audio in the recording, or maybe I'll completely replace it with the original. Whatever, that's normally what I do. But since this is directly being funneled into the recording, it's probably okay the way it is. Okay, so let's say how water dissolves salt. I don't think this is narrated. Okay, there's the salt. All right, so what are we looking at? The yellow, they're the smaller ions. Those will be sodium. Right? Sodium has lost electrons. It's Na+, makes it smaller. Chloride has gained an electron from sodium, so it's ballooned out. That's why it's the bigger one. So there comes the water molecule. Right? The hydrogens are the reds. Yep. That shows the polarity. So what's it going to be attracted to? That could be either one. It depends on its orientation. So there the positives are attracted to the negative chlorides. They pull them out. Then the negative side is attracted to the sodiums that pull them out. This is called the process of hydration. And in solution, they're associated that way. Opposite charges. Keeps them in solution. And eventually, the crystal of sodium chloride is ripped apart. Okay. So when we talk about solutions, we need some agreed upon terms. If you haven't heard of these before, the solute is the substance that's being dissolved. It's usually the minor component, the smaller amount. The solvent is the substance that's doing the dissolving, in this case, water. Now, there are some cases where you start off with a small amount of solute going into the solvent. And if you just keep adding solute, and it's very soluble, then you may eventually end up with more solute than you do have solvent. Right? Anybody has made hummingbird food, right? Dissolve sugar in water. Standard is half and half, but you can go higher than that. You can put more sugar in there than there is water, and it'll go into solution. But when we say solute, that's our starting point. So we're putting sugar into the water, small amount at first, that makes it the solute, no matter how much you have. An electrolyte is any substance that's dissolved in water and can conduct electricity. So if you dissolve sodium chloride in water, why does it conduct electricity? Right? You have a pile of sodium chloride down here. What if you have a crystal of sodium chloride? Right? Will it conduct electricity? Right? Put an electrode in here, put an electrode in here, and you try to apply it. Well, I left out the battery. Try to apply a charge to it. Will you get register on the meter? Nope. You have to have mobile ions. In other words, you've got to complete the circuit, right? All electrical circuits, they go like this. That's why they call them circuits, because they go in circles, right? So this crystal will not conduct electricity. But when you put in water, now you have sodium ions and chloride ions. They will conduct a charge. They will take the current through the solution out. So if we did the same thing over here, you would get that, or if you had a light bulb, it would light. That's why electrolytes conduct electricity, because they break apart into individual ions and can, that's the avenue for transferring current from one electrode to the other is through the ions. So if you took this sodium chloride crystal and melted it, it would be electrolyte then, except it wouldn't be dissolved in anything, but it would still conduct a charge because now the ions are free to move around. They're in liquid form. In solid form, they're locked in place, but in liquid form, they can move. So you can conduct electricity through sodium chloride. And in fact, that's the way they get sodium metal and chlorine gas, is they electrolytically break it apart. They make it into a liquid, and then they run a very high current, high voltage charge through it, and it attracts chlorides to the positive pole and sodium to the negative pole, and you get sodium metal and chloride gas, chlorine gas. And you can do a lot of other stuff with it after that.
Why, after like you work out or something, you need electrolytes? Why does your body need?
Because the sweat that you produce to stay cool is not just water. It has these ions in it too. So you're expelling ions from your body when you exercise because you're sweating them out. So the more you sweat, the more you have to replace.
So can electrolytes be found in sugar, so like sugary stuff?
No, because sugar does not dissociate into free ions. Sugar is fructose and glucose hooked together, and they're molecular. They're not ionic. So when you put them in solution, they will dissolve in solution. They will go into water, but they don't make ions. Okay, so they're not electrolytes. And when you get blood work or urinalysis and the doctor looks at it, they've got the electrolytes in one place and some other stuff. But the electrolytes are usually sodium, potassium, maybe calcium, magnesium, chloride, and some others, some minor components. Those are all in your body, they're all ions. And your muscles and nerves don't function very well if you're short on ions, sodium and potassium in particular, because that's how they work. They work by transferring those charges across the membranes of the muscle cells or the nerve cells. And if you don't have enough, if you're out of balance, then nothing works right. Okay, so this is a qualitative differential. Strong electrolytes conduct a lot more current. In fact, sodium chloride would be a strong electrolyte. It completely dissolves, makes lots of ions, will conduct charge very readily through the solution. That's a strong electrolyte. Weak electrolytes, they dissociate sort of, a little bit, but not completely. So when you put the same amount of a weak electrolyte as a strong electrolyte, you get a weaker signal coming through. Some of the acids, organic acids in particular, will partially dissociate and make some ions, but not many, like acetic acid. Vinegar is a weak electrolyte. Non-electrolytes are like sugar. They don't dissociate at all. So if you're trying to light a light bulb by putting your electrodes in this solution to conduct electricity, it won't work for non-electrolytes. Oh, we got another video.
We know from various lines of experimental evidence that solid sodium chloride consists of an ordered three-dimensional array of sodium and chloride ions. Solid sodium chloride is not a conductor of electricity. The ions of the ionic lattice are held in place by these strong ionic interactions in the solid and therefore are not free to move under the influence of the electric field. When sodium chloride is dissolved in water, it forms a solution of separated sodium and chloride ions. The presence of ions in the solution is responsible for the fact that the solution is a conductor of electricity. Substances such as sodium chloride that exist in aqueous solution entirely or nearly entirely as ions are called strong electrolytes. By contrast, an aqueous solution of a non-electrolyte, such as sugar, does not conduct electricity.
All right. I probably should have let her do the explaining. Save me the trouble. Okay. So we have chemical reactions that occur in solutions. That's possible. So we need to know the nature of the reaction, just like any chemical reaction. And we need to know the amount of each of the reactants that are present in the solution. Right, so we need a way to express concentrations. Because if we know the concentration of each of the reactants in the solution, then if we measure out a certain volume of that solution, we can calculate how much of the reactant we're delivering. Molarity is a very common way of expressing a solution concentration. And it's very simple. It's like any equation. Molarity equals moles of whatever per liter. Moles per unit volume. In this case, it has to be liters. Okay, so if we have 6 moles of hydrogen chloride dissolved in water, which makes it what? Hydrochloric acid. And the total volume is 2 liters. Now that's the volume of the solution after you add the solute into it. Then we know that we have a 3 molar concentration of HCl in that solution. Notice that if you have 3 molar, what does that say? That equals 3 moles of HCl per liter. So if you want to subsample that and say take out not a liter, but say 1/10 of a liter, 100 milliliters. Times that, then that means we would have 3 moles of HCl in our possession with that volume. Okay? It's a very convenient way of expressing concentrations. All right. This particular slide is making a point of the fact that if you put 500 grams of potassium phosphate in water and make it up to 1.5 liters, what's the molarity? You can't directly calculate it because it's in grams, not moles. Right? So how do you get moles out of that? Well, 500 grams of what? Potassium phosphate. So you have to know how to write the compound. Got to remember that. 500 grams of that, you can convert it to moles using the molar mass of the compound. Now that you have the moles, you can put it in the formula, divide it by 1.5 liters, and produce 1.57 molar concentration. Okay. Now we're assuming that potassium phosphate is soluble. And in fact, it is. And I'm going to give you some rules to go by to know whether your ionic compound is soluble in water or not. If you're expressing the molarity of the compound, in this case, 0.25 molar calcium chloride, that's 0.25 moles of calcium chloride per liter of solution. What would that be in terms of the ions? Because if this goes into solution, it's not calcium chloride anymore. It's calcium ions and chloride ions, right? So the concentration of calcium would be the same as the molecule, right? Because for every 1 mole of calcium chloride, you have 1 mole of calcium. So the concentration would be the same for the calcium ions. But the chloride ions, you've got 2 chlorides for every 1 calcium chloride. So the concentration of chloride ions would be double, be twice that much, 0.5 molar. Okay? That's important, particularly if you're going into the medical profession. Well, it's not as important now because everything's pre-made for you. But when they had to calculate these for themselves and produce an isotonic solution for their patients, right? You don't want to put a hypertonic or hypotonic solution in your patient's veins. It'll kill them. So you need to know, how do you calculate an isotonic solution if you got all these different ions in there, okay? I guess they decided it wasn't worth the risk to train their nurses and doctors and then expect them to do it right every time. So they get a laboratory to generate the products in sterilized bags, and you just hang the bag and stick it in your patient. I guess that's safer in the long run. Which one contains the greatest number of ions? Well, remember, molarity equals moles per liter or unit volume. So if we're looking at the number of ions, we want to know that value right there. So we just rearrange the equation. So the number of moles equals the molarity times the volume. Okay? Now, when we're using this equation, the volume has to be in liters. So that first one, well, all of them have to be changed. 400 milliliters is how many liters? How many milliliters in a liter? Let's put it that way. 1,000, right? So if the unit's going to get bigger, we're going to go from milliliters to liters. The number has to get smaller. Right? So which way would the decimal have to move? That way. And you move it 3 places, which is equal to 1,000. Right? So 400 milliliters would be 0.4 plus the zeros. And the rest of them would be 0.3, 0.2, 0.8. Okay? So once you've got the number of liters, you can multiply by the concentration, and the concentrations are all the same, 0.1 molar. So that tells you how many moles of a compound you have. But how about the ions? Right, it's 5 o'clock. So if you have to go, I'll just keep talking. If you can stay, that's fine. If you can't, then I'll post the video. So this first one would be 0.4 times, and this is liters, times 0.1 molar. Right, so how many moles of the compound would you have? 0.04 moles, right? How many moles of ions would you have? For every one of these, you have 2, 1 sodium, 1 chloride. So sodium chloride would be times 2, 0.08 ions. And you do that same thing for each one. The next one would be 0.03 times 3, 0.9. The next one would be 0.02. Yeah. Times 4, and that would be 0.08. And then the last one, would it produce any ions? No, sucrose doesn't do that. Right, so you can say greatest number of ions. This one, the second one, calcium chloride. Okay. Okay, we talked about that before. You got to do the calculation to find out, to answer the question. You can't just eyeball it. Okay. So now that we know the relationship, I mean, the formula for molarity, sometimes it's practical if you got to do lots of analyses with the same solution. It's practical to make a batch of concentrated solution. And then when you need some, you take some of that and dilute it to the right concentration. So this is the formula that you use. Or you could write it this way. That's the concentrated, and this is the dilute. Okay? So if you know the concentrated, you know this is the molarity of your concentrated solution. This is the volume that you need of the diluted solution, and this is the concentration of the diluted solution. Then you've got 3 values and 1 unknown you can solve for. What volume of the concentrated do you need to dilute to that volume to give you this concentration? We used to do that in the soil testing lab because we had hundreds of samples to extract every day with a dilute solution. So we'd have a concentrated solution and just fresh every day, we just make up a new batch with our concentrated solution and go get some poor student worker to do the analysis. But why does this work? That's the question. Why does that work? If you look at it this way, like with pictures, you've got this concentrated. This is the molarity of the concentrated. And this is going to be that's a volumetric flask. It's guaranteed, if you fill it up to that mark, it's guaranteed to have a certain volume in it. So for argument's sake, let's just say it's 1 liter. So if our volume is 1 liter, our concentration would be whatever, say 0.5 molar. And over here, we have a concentration of, say, I don't know, 10 molar. Then you need to take an aliquot out of this one and deliver it in here and dilute it to the mark, right? So when you take that much out of here and put it in there, what changed? Location. That's it. The number of moles of your solute from here to here did not change. It's exactly the same number of moles, right? So if this tells you the number of moles from the concentrated is equal to the moles of the dilute. And that's what this is, right? M times V equals moles per unit volume. So M times V equals moles. So if this is concentrated, and that's equal to dilute, that's why you can say this is equal to that, because those two are exactly equal. That's why dilution works. All right. Okay, I've got a slide on it here, so I'll just go through the animation, right? It says the same thing I just put on the board. Okay. If you have a 0.5 molar solution of sodium chloride in a beaker, sit it on the lab bench and it's open to the air, which of the following would decrease the concentration of the salt solution? Add water to the solution. Would that decrease its concentration? Yep. You put more solvent in there, which makes the solute more dilute. So A is true. Pour some of the solution down the sink. I don't know why I did that. I bet I know why. In Zoom, if you run too long, it makes a recording up to a certain number of gigabytes. And then it stops and starts a new file. So I bet when it stopped and started a new file, it kicked me off. Okay. What's the minimum volume of 2 molar sodium hydroxide solution needed to make 150 milliliters of 0.8 molar sodium hydroxide solution? This is your formula. Right? So what you have to do is decide which one's which. Which one's concentrated? 2 molar. This one is unknown. That answers the question. 150 milliliters of 0.8. So we need this interesting thing about this formula. Notice that if you put milliliters in here, that answer will come out as milliliters. If you put liters in here, it'll come out as liters, right? So we can put 150 milliliters here because it's a ratio. You get the same units in there as you did over here. Saves you some effort. Oh, this is illustrating. It's probably a good idea, especially if you're in the heat of an exam, to make a list and put the items in there where they belong. Then you can use the formula and not make a mistake. So I went directly to this, but sometimes it's better to make your list first and then plug the numbers in. So the volume would be 60 milliliters. If we had used liters, it would come out as 0.060 liters. All right. Types of chemical reactions. These are to help us categorize reactions and know how to treat the reaction. But many reactions are a combination. They can be classified as one or both or maybe 3 types. It's possible. And in your review doc, these are examples. So we need to go to subsequent slides to talk about the individual types. Precipitation reaction is also a double replacement. What that means is when you put the 2 solutions together and they react, sometimes they make a compound that's not soluble anymore. And it forms a precipitate, which is a solid, an insoluble solid in the solution. And that comes about from the reaction itself. And it's a double replacement because if you put this one in solution and then you put it together with this one in solution, then they swap places, double replacement. This one goes over here and that one goes over here. So this would be AD plus CB. Now we don't know which one. If we get a precipitate over here, if you don't get a precipitate, then there's no reaction. But if you get a precipitate, then one of these should drop out as a solid. Now I've got a, let's see. Yeah, review document. If you look at on the back page right here, show it to the camera. There's this chart, and across the top are the positive ions, and across the left-hand side, down the left-hand side, are the negative ions. So if you follow the positives down to where they meet the negatives and you find a block, if it's clear, that means it's soluble in water. If it's grayed out, that means it's insoluble in water. And these are the rules that we go by at the bottom. But you're going to have access to this table, so you don't have to learn the rules. Unless you want to. If you're going to major in chemistry, you ought to learn them. But if you're not, then just use that chart, and it'll tell you whether this product or that product is insoluble in water. Here's an example. Barium nitrate is soluble in water, right? In fact, the rule says all nitrates are soluble. Potassium chromate, the other one, that's soluble in water. All alkali metal compounds are soluble in water. Potassium's an alkali metal. But when you put them together, right, they're broken apart into ions. Barium ions, nitrate ions, potassium ions, chromate ions. So they can interact. So when the barium finds a chromate, it latches on, drops out of solution. Okay, the barium chromate is solid. The potassium nitrate is still soluble. Okay, and you can look that up on that table. If you follow barium here and then look at chromate, follow the box is grayed out. May not be any narration on this one. Those are two separate solutions, right? Sodium chloride and silver nitrate. They're both soluble in water. You add them together. What are the possibilities? The silver ions can combine with the chloride ions. And the sodium can combine with the nitrates. You look it up, this one is soluble. This one is not. Makes a solid. So that white precipitate is silver chloride. Okay? Oh, some precipitate reactions. There you go. Shouldn't take too long. Silver nitrate and sodium thiosulfate. Thiosulfate and silver form a precipitate, but it's a different color than the silver chloride. Let's see, barium and sulfate. That's the solid. Anybody who's had a barium enema to have an x-ray done of your lower gut, that's what they put in you. Barium sulfate. And the reason they do it is because it's insoluble. It won't dissolve and go into your system. Copper hydroxide sulfate. Okay, I just thought that was pretty pictures. Okay, so we classify soluble and we put an AQ next to it. That says that compound is soluble. We put an S next to it. That means it's a solid. And it's, if you give it enough time, it will settle out on the bottom of the beaker. Now, we're talking as if there's a very fine, there's a solid line between soluble and insoluble. Fact of the matter is, there's a gray area between soluble and insoluble. So insoluble may be slightly soluble, but for right now, we're calling it insoluble. Okay, we'll talk about how to calculate the solubility of an insoluble compound later. Okay, these are the rules, and all you need to know is that these rules are set up so that if you have a decision to make on the solubility of a compound, you look at the two or more rules. If more than one rule applies, the one above takes precedence. So that means any nitrate salt, any cation, positive ion, with nitrate is soluble. It doesn't matter what these other rules say. Okay. Which of these compounds are generally soluble in water? Lead compounds. Well, you look at your chart, right? Take lead from the top and run down till you find sulfide. Run down till you find chloride, nitrate, sulfate, and see which are soluble and which are insoluble. And E is thrown in there as a ringer. You don't form compound with two cations, right? They're both positive. They don't form a compound. So E you throw out right now. But if you go looking, you find that the nitrate is soluble because all nitrates are soluble. But the rest form insoluble compounds with lead. The sulfide, the chloride, the sulfate, they're all insoluble. Okay. So when we write these reactions, this is a generic, but when we actually write them, they can take three forms. The formula equation or the molecular equation has everything. You say this compound aqueous, this compound aqueous yields. This compound, maybe it's solid. This maybe it's aqueous. Right? You just write the formulas out with their phases. That's the molecular compound. And here's your example. Silver nitrate plus sodium chloride yields silver chloride solid plus sodium nitrate aqueous. That's the formula equation, or the molecular equation, sometimes we call it. But you know that when it's in solution, silver nitrate is silver ions and nitrate ions. Sodium ions and chloride ions, right? So this is an abbreviated form. This is not reality. Reality is individual ions. The only one that's true out of this is silver chloride solid, right? So if you write it in terms of all the individual ions, the ionic equation, the complete ionic equation, it will look like that. Okay, that's reality. Silver ions, nitrate ions, sodium ions, chloride ions makes silver chloride solid, and sodium ions and nitrate ions are still there, floating around in the water. Right? So, what do? Well, if we've got nitrate ions on the reactant side, nitrate ions on the product side, they cancel each other out. They're not even part of the reaction. They're called spectators. And sodium is also a spectator. It's still ions on both sides of the equation. So if you take those out, now we have the net ionic equation. So really the equation that you're interested in is silver ions plus chloride ions makes a solid silver chloride. Now, what's the advantage to that? Well, suppose you're an instructor and you got to make up a solution for your students that will illustrate this reaction. Well, suppose I don't have any sodium chloride, but I do have potassium chloride. It's soluble in water. Potassium and nitrate are still soluble. So the potassium becomes the spectator along with nitrate as spectator, and you got the same net equation, exactly the same. Okay? That's one possible scenario. Here's another example. The formula equation, you just write it out, right? If it's a double replacement, you write it out so that you indicate which is the solid that's formed, and what's left over, in this case, is the sodium chloride. Put the phases in there. Then once you've got the equation balanced, and you balance it the same way as any other equation, then you split the ions out. Notice that cobalt 2+ is the charge, right? You need to know that. Chloride -1 is the charge, but there are two of them. So now the subscript of COCl2 becomes the coefficient for the chloride ions. Okay, same thing for sodium hydroxide. You got 2 sodiums and 2 hydroxides. Then you bring them together and you do the same thing on the product side. That's your complete ionic equation. Then you just look for common ions on both sides, cancel them out, and that's your net equation. That's the business end of the equation. Cobalt plus hydroxide makes cobalt hydroxide solid. That's your net ionic equation. In fact, that's what drives the reaction. Because as you form that solid, it drops out. It's no longer part of the medium. So it just keeps going until one of them is all used up. And you can still have limiting reactants, right? If you don't have enough cobalt chloride, then as soon as it's used up, the reaction stops. Okay? So when we solve stoichiometry problems for solutions, it's similar to what we've done so far. You still have to find the number of moles in order to go anywhere in your equation, but you find the number of moles differently. Right? If you have a solution that's a certain molar concentration, and you're told you put this so many milliliters of that together with some other solution, then you need to find out how many moles that is. Right? So you would say 0.025 liters times this. That gives you the number of moles. Now you can move. Okay? It's just a different way of finding the moles. Rather than using molar mass, we used our equation for molarity. Okay? The thing about it is, once you find out how many moles of product you got, if you have moles of spectators, or you have moles of the solid, then the moles of the spectators, you would recalculate them in terms of molarity, taking into account that you've added volume from both here and here. So the volume on this side would be the sum of these two. And then how do you find the moles or the mass of your solid product? Same way we did before. If you know the moles, then you take the molar mass of the product and find the moles, find the mass, excuse me. Okay? Okay, there's your chart. And we're not going to go over it because we already hammered that one. Let's see. I'm trying to see how far I've gone. And I got a little ways to go. Okay, so let me speed it up. All right. So I can't speed it up too much. Otherwise, it'll just become a jumble. But this is a word problem, right? So you're given so many milliliters of a concentration of sodium phosphate. First thing you need to do is write sodium phosphate. That's a polyatomic ion with a 3-, so that means with this 1+, you need 3 of them. So that's an aqueous solution. It is mixed with what? Lead 2 nitrate. Right? So we need 2 of those. And this is aqueous. Okay, when we put those together, what do we get? Well, it's a double replacement reaction. Sodium reacts with nitrate, which makes what? Is soluble, right? And then lead reacts with phosphate. And the charge does not change. That's 2+. This is 3-. So we need the 3 over here and the 2 over there. Okay? And then you look it up in your chart and you find that this is a solid. So to answer the first question, the precipitate that forms is lead 2 phosphate. Oh, I thought it was going to tell us. Now, the mass that forms, that takes a little more work. 10 milliliters of this one, 10 milliliters of 0.3 molar, and this one is 20 milliliters of 0.2 molar. Okay? So something I haven't told you yet. I alluded to it when I said you don't have to change the milliliters to liters when you do the dilution. If you multiply this times milliliters, you don't get moles, you get millimoles. So 10 times that would be 3. This would be 3.0 millimoles. That kind of shortens things. And this one would be 20 times 0.2 is 4, right? 4 millimoles. Yeah, 4. Okay, now that you've got the number of millimoles, eventually we're going to have to convert those to moles, because to answer that question, we have to find out which one is limiting. And we haven't talked about that yet, have we? How to find the limiting reactant. All right, so let's convert this to moles. So if a unit gets bigger, that has to get smaller, right? Milli is 1,000th. So we got to move it 3 places. Moles. Okay, this one would be 0.040 moles. All right. So how do you find out which one's limiting? The one that runs out first. So you have to take each one and say, what if I have an excess of this one and I use all this one up? How much of this product will it give me? So this is 0.0030 moles. And is this balanced? Oh, no, we didn't balance the equation yet, did we? Sodium, phosphorus. We got 3 sodiums. We got 3 leads. That makes 6 nitrates. Wait a minute. I'm trying to do this in my head. Let's see if it balances the equation for us. All right, we'll save ourselves some time. So 6 here and 3 here. Three there, 2 here, 6 there, and 1 here. Okay, so now we're balanced. So now what you have to do is say, all right, how much of this would form from that? Actually, we can still use 3 millimoles, because moles is moles, going anywhere in the equation. 3 millimoles of this would do what? Well, 3 millimoles of that reactant ratio to what? Well, we want to get rid of that one, so we're going to put 2 down here. And we're going to have 1 up here. So half of that, 1.5 millimoles from here. From here, if we have 4 millimoles, what's the ratio there? Well, we're going to get rid of 3 here and end up with 1 there. So a third of that would be 1.33. Which one runs out first? The one that makes the least amount. So this one makes the least amount. It runs out first. That means that we're going to have 1.33 millimoles of lead to phosphate. Okay. All right, here we go. Okay, now we've done a calculation for this one, this one. And we do the calculation for the other one, there's 1.33. So we know that that's the true amount that's formed. It's the least amount. All right. So that's the millimoles of lead 2 phosphate that's formed. Was the question concentration? What mass will be formed? Okay. So in this case, we need to convert this to moles now, which would be 1.33 times 10 to the minus third moles. Okay. We need to divide it by 1,000. And then convert that, and we get 1.08 grams. Okay, did I go too fast? Work some problems and come back next Friday and give me the bad news. Okay, so that's the stoichiometry of precipitation reactions. If we had done this in a way where we were saying, what's the concentration of sodium that's left in solution? Well, we start with the one that runs out. Well, actually, since they're spectators, all we need to know is what's the concentration of sodium, right? The concentration of sodium is 3 times that, which is 9 millimoles of sodium. So 9 millimoles of sodium should be over here. 9 millimoles divided by the total volume, which is what? 30 milliliters. And if you take millimoles and divide by milliliters, you get molarity, right? Because that's milli and that's milli, cancel them out, it's still moles per liter. Okay? Gotta go?
No.
Okay. All right, so we got some other types of reactions. Those were double replacement precipitation reactions. We've got acid-base reactions, and they're denoted by the fact that the net ionic reaction is protons or hydrogen ions plus hydroxyl ions makes water. That's the net reaction for an acid-base reaction. Oh, got another video.
Hydrochloric acid contains hydrogen ions and chloride ions in aqueous solution. Sodium hydroxide contains sodium ions and hydroxide ions in aqueous solution. When these two solutions combine, a neutralization reaction takes place. In this reaction, hydrogen ions from the acid and hydroxide ions from the base combine to form water molecules. The sodium and chloride ions are unaffected and remain to form a neutral sodium chloride solution. Neutralization can be summed up by this simple ionic equation.
Okay. So what you're looking for in an acid-base reaction is an acid. We know how to write an acid, right? It starts with a hydrogen, and that hydrogen is the one that dissociates. So remember when we were naming that, naming this, naming this one, so forth. You got the hydrogens, and they're the ones that dissociate. And then if you put a base in water, it splits off the hydroxyl, right? And this positive reacts with that negative and makes water. Okay, that's an acid-base reaction. An acid-base titration, which we are going to do in the lab, is one in which you have either a known amount of acid or a known amount of hydroxyl. And for the known amount, you put a known volume. So you know the concentration, you know the volume, you know the number of moles of either this or that. And then you take the unknown solution and you keep adding it to one or the other until you detect a point at which they're stoichiometrically equal. That's the equivalence point. And if you have an indicator that'll tell you when you get there, then you can take the volume you delivered from the unknown and solve the equation. Because the molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. Now this only works if they're one hydroxyl and one hydrogen per molecule. Otherwise, you've got to throw an adjustment factor in there for, like if you had, say, two of these, then you'd have to accommodate it, say, you need twice as much base, right? But we'll talk about that later. That's the equivalence point, when exactly the same number of hydrogen ions match the number of hydroxyl ions. And that you can detect that by doing the titration and measuring the pH, the acidity, and plotting the curve. You can find exactly where that equivalence point is. But you can't do that for every titration. Say you have 100 titrations to do for your lab. So we substitute a color change agent called an indicator. And it's chosen to change colors at very close to the equivalence point. As it turns out, it doesn't have to be exact to give you good results. So the endpoint is what the indicator says is the equivalence point, okay? That's the difference between the two. Let's see. All right, I'm gonna blast through the rest of them. Acid-base reaction, all right, we're gonna go through that. Redox reaction. What's a redox reaction? We're gonna talk about those in more detail later, but for now, a redox reaction is any one in which electrons are transferred during the reaction. So if you get, for instance, if you have sodium metal and chlorine gas, and you react them together, you get sodium chloride, solid, and we need to balance these. So that's 2 there, 2 here. Okay, notice that this is neutral and that's neutral. But what are the charges over here? This one's a +1 and that's -1. Right? So what happens? Electrons had to be transferred from the sodium to the chloride. That's a redox reaction. Oxidation reduction is the expression. The species that loses electrons is oxidized, and the species that gains electrons is reduced. That's why it's called redox. But we'll talk about those in detail later. All you need to know is that electrons are transferred. And in order to determine whether electrons are transferred, we use this bookkeeping method, oxidation states, right? And these are the rules that go with it. The oxidation state of an atom in an element is 0. So the sodium was 0, the chlorine was 0, any element from the periodic table is 0. So you say, it's kind of like charge, but not exactly. It doesn't have to be charged. Sometimes it is. The oxidation state of a monatomic ion is the charge on the ion. So if we have, say, a solution where you have individual ions, then the charge on that ion is its oxidation number. In most compounds, oxygen is given an oxidation number of -2. So for water, this would be -2. oxidation state. And that means hydrogen would have to be an oxidation state of +1 because there are two of them to balance. And that's the case with most hydrogen compounds. Hydrogen will be +1 unless it's combined with a metal, right? One of those examples. Well, no, you haven't. Yeah, you've done named compounds, the extra credit. Okay. Wasn't there one in there that was like this? Sodium hydride. Okay, in this case, sodium is the plus and hydrogen is the minus. In those cases, hydrogen is -1. But in all other cases, and particularly when hydrogen is first in the name, it's +1. Fluorine is always -1. And usually the halogens are -1 also, but not always. The sum of the oxidation states for a neutral compound has to be 0, right? Because the compound is neutral. They have to add up to 0. The oxidation states for, well, we said this before, of an ion is the charge on the ion, but the oxidation states for all of the components of a polyatomic ion, like this one, have to add up to the charge on the ion, right? So if oxygen is -2 for each one, -6 total, right? 2 times 3. That means this one would be, if it were neutral, this one would be +6. But we need to hold out one of those negative charges for that. So it really only has to balance 5. So +5, -6 is -1. That's how you balance it. They add up to the charge on the polyatomic ion. Okay, oxidation states here. What you need to do is for the polyatomic that carbonate with 2- charge, do the same type of calculation. Once you get down to here, say, okay, how many negatives do I need to keep? Right? If it were -6, in that case it is, then you would need -4 and leave 2 minuses out here. So +4 would be the carbon. And for the others, they're all neutral. So you just use the ones that you know, oxygens, potassium, all of the alkali metals are +1, all the alkaline earths are +2. Chloride for a PCl5, chloride should be -1. Then you can calculate phosphorus, which would be +5. Right? So there they are calculated using that method. All right. All right, I mentioned this already. Redox characteristics, transfer of electrons. You can form ions, but you don't have to form ions to get a redox reaction. That's why we have that oxidation state calculation. Because if you've got molecular compounds, neutral compounds on both sides, and you know there are no ions in them, how do you know if electrons are transferred? That's why the oxidation state method was developed, to keep track of the electrons. So oxidation is an increase in oxidation state, which is loss of electrons. And notice that when you have something that, say, this one plus this one yields something, and you transfer electrons like that, this one is oxidized, this one is reduced. That makes this one the reducing agent. It causes the reduction of B. So the oxidized species is the reducing agent, and the reduced species is the oxidizing agent. Okay. Identify the oxidizing agent, the reducing agent in each one of these. Well, what we've done here is we've looked at the oxidation numbers for each of the elements and say, did they change from one side to the other? There's a rule of thumb here that's very useful. If you have on one side here, you have an element, which is 0 oxidation number. But it ends up in a compound on the other side, it's automatically oxidation reduction. It has to be. Or if it's an element on that side, like hydrogen over here, and it originated from a compound, that's oxidation reduction too. Okay? That's just a rule of thumb. The others, you have to actually calculate the oxidation numbers and see if any of them changed. So for these two, this one didn't change, but I think this one will change. C does change. Now C is a unique type of reaction. Cl yields CuCl2 plus Cu, right? Okay. Notice that we've got copper in two different places over here, but it's only in one place over here. So if this is -1, this has to be +1. We're doing oxidation numbers. This one is 0, right? This one is -1, so this one has to be +2. So notice that one of these coppers, there are two of them, right? One of these coppers went to here, and the other one went to there. Okay, so I like to draw it this way. This is loss of 1 electron per copper. This one is gain of 1 electron per copper, right? Because if you gain 1 electron, you neutralize it to 0. This is called a disproportionation. Reaction. When you get the reaction going in two different directions. Okay, so let's see. Balancing redox reactions. That's the last item on the table here. Okay, when we balance the redox reactions, the first thing you need to balance is the electrons. You got to balance the electrons, then the rest of it will fall into place. If you try to balance it without considering the electrons, maybe it'll work and maybe it won't. Right? Sometimes it will work. But if you balance the electrons, then you're pretty much guaranteed to get it balanced the easiest way. So balance the reaction between, let's see, solid zinc and aqueous hydrochloric acid. Solid zinc and aqueous hydrochloric acid. What does it produce? It produces aqueous zinc 2 chloride. Right? That has to be 2 plus because it said it's zinc 2. And hydrogen gas. Right? You have to know it's diatomic. Okay, so now we need to balance that. If we're going to balance it as a redox reaction, and we know it is, hydrogen is in a compound here, it's an element there. Zinc is an element here, it's in a compound there. So we know it's a redox reaction. This one is oxidation state 0, this one's 0. This one is +1, this one's -1, this one's +2 because they told us it was, this one's -1. Okay, so now you have to decide which one's oxidation and which one's reduction. Right? Zinc goes to zinc. What has happened to the zinc? It lost 2 electrons, didn't it? That's the only way you can get a change in charge. You can't do it with protons. So loss 2 electrons per zinc. How about hydrogen change? Chloride didn't change at all, but hydrogen did. Okay. So what does it do? Well, if this is lost, this must be gain. Gain 1 electron. So 1 electron plus a positive will make a 0. gain 1 electron per hydrogen. Okay, now we need to balance. When you oxidize a certain number of electrons, you have to reduce with the same number of electrons. They must balance. So if this is 2, we need 2 down here, don't we? So if we say times 2, what does that mean? That means 2 here and 2 there already. Okay? So that means that we have gained 2 electrons. Now the electrons balance. And all we need to do now is see, all right, do we need to do any more balancing? Sometimes you do, sometimes you don't. 1 zinc, 1 zinc, 2 hydrogens, 2 hydrogens, 2 chlorides, 2 chlorides. It's balanced. Okay? And these are the steps that you would go through in animated form. Ooh, it's almost 6 o'clock. We have everybody driving home in the dark. Okay. That's it.